positioning, horizontal accuracy, and vertical accuracy.
This meeting is being recorded.
All right. And the positioning service availability and the positioning service latency from level 1 to level 7. And in the recent years, that another KPI has been added into a 3GPP positioning system is the power consumption, as listed in the right-hand side of the figure. On top of the existing positioning service level, including the accuracy and latency, another key performance indicator KPI, battery life, has been added. There are multiple use cases for the low power, high accuracy positioning use cases, including use case 1 to use case 9, and ranging from a work of battery life to more than 5 years. So in order to develop the solution to meet the corresponding requirement, 3GPP has been working on positioning ever since its first release 15, for NR and for 5G. So here's the brief history of the 5G positioning evolution. Yeah.
Just one question.
Yes.
I didn't see you. Did you scroll your screen? I didn't see any page movement.
Oh, all right. Maybe like let me try something else.
You can try display model.
So, can you see?
Yes.
See the release
okay.
15 to release 18? All right.
Yes.
Maybe there's something wrong with it. All right. So in release 15, because it's the first release of the NR interface, that the 5G positioning mainly relies on LTE solutions, because by that time, NR working groups are still working on the basic communication services. So that we use the 5G non-standalone deployment using, for example, the 5G core network, rely on the LTE base station that is connected to 5G core network, so that LTE existing solutions can be used to position the UE. And this is the basic functionality of 5G positioning to meet the local regulatory requirements. And in release 16, it is the first version of the NR positioning. It's targeting regulatory requirements from 15 meters at 80%. And in addition to the regulatory requirement, 2 commercial use cases being added, from 10 meters at 80% for horizontal accuracy for outdoor environment, and 3 meters for indoor requirement. And since it's the first release of the NR positioning, the positioning using NR interface, a new reference signal and a physical layer measurement and procedure were defined. In release 17, the positioning being involved to meet the stringent requirement of industry IoT, where 0.2 and 0.5 meters horizontal accuracy are proposed or are the targets. And in addition to the accuracy requirement, low latency being also proposed, being also studied to meet the 10 millisecond end-to-end latency requirements. On top of it, accuracy improvement, latency reduction, and power efficient improvement have been standardized in release 17, which is just closed, which is increased in June this year. Now it's the time for release 18, which is the third version of NR positioning to expand the position scope, including the NR settling positioning, low power, high accuracy positioning, and the various solutions to improve the positioning accuracy, for example, using interband bandwidth aggregation in our carrier phase positioning. New support of the release 17 red cap UE positioning has also been proposed. Integrity support has been since release 17, where the GNSS integrity was standardized in release 17. Now release 18 has been exploring the NR positioning integrity. It is worth noting that release 18 NR positioning is still under the study phase, and the normative phase is expected to start in 2023. So let's take a look at the 5G positioning architecture. In order to build a very secure system, 5G positioning have a strict boundary between UE, radio access network, and a core network. The radio access network are composed of the 5G base station G node B, as well as the AOT base station that is connected to 5G core network, which is referred to as NG E node B. So both G node B and E node B are part of the 5G positioning architecture in the RAN side, radio access network side. In the core network side, there resides a location server, location management function, LMF, which is routed by the AMF to have access to the RAN network, to the RAN side and the UE side. There are other entities in the CN network to handle for example, the LCS request and the user authorization data. 5G positioning has been has support 3 types of location service early from the first release. The first one is the 1A MTLR, which is the mobile terminated location request. It is typically driven from a third party, which requests location information of targeted UE. And the second one is the network induced location request. It is typically for emergency call to meet some regulatory requirements. For example, when the AMF receives the emergency PDU from a UE, will automatically generate the network induced location request pending on local authority. And the third one is mobile originated location request. It's typically a UE requests its own location from the 5G core network because, for example, a user wants to know its own location for a UE, and it can trigger some MOLR to the core network. When the AMF has handled or initiated the location request, it finds the proper location server, AMF. Then what work related to 3GPP RAN working groups is to starting the procedure involving AMF, the NG RAN node, the G node B or NGE node B, and the UE on the NG RAN node procedures and UE procedure to help the location server or help the UE to find the location of a specific UE. When the location has been obtained, when the AMF obtains the location, it returns the location service response to the AMF, and the AMF dispatch the location response to the initiating entity. In release 16, the following 6 solutions positioning methods is being standardized in NR, 3 of which are simply evolution of LTE solutions. NR ECID is an evolution of LTE ECID. NR downlink TDOA is the evolution of LTE OTDOA, and NR uplink TDOA is the evolution of LTE UTDOA. And on top of it, NR also introduced 3 additional positioning methods. One is uplink AOA, the other is downlink AOD, the third is multi-cell RTT. So for downlink TDOA, multiple TRP or the GNOB is transmitting PIs at the same time. If we assume the perfect synchronization between TRPs, the reference signal receive time difference between a pair of the TRP will corresponding to the distance difference between the pair of TRPs, and we using this measurement to help the positioning location fixed entity to know that UE is somehow located in a hyperbola or hyperboloid, with the foci being the location of the 2 TRP. Then if we add another pair of TRP, another hyperbola, a hyperboloid will be drawn, and the multiple hyperbolae create an intersection that provides the estimate of the UE location. In general, downlink TDOA will have a stringent requirement of the network synchronization, but there are other ways to improve that or relax. For example, you can use some correction UE to help identify the synchronization error between the TRPs, which is currently beyond 3GPP scope. Likewise, for uplink TDOA, the transmission, the reference signal link is different from the downlink, where the UE is transmitting something and network is to receive the SRS. So in general, the positioning methods are the same as the downlink TDOA, except for the uplink part. But the uplink part is more attractive than downlink because it only requires UE to transmit SRS, transmit some uplink signal, so that it can be support even for legacy UE, so that we can upgrade the network to support the release 16 positioning feature. But even for release 15 UE, which does not support positioning at all, can also be positioning using this method. Can also be positioned using this method, as long as it's able to transmit any legacy signal that can be received or can be understood by the GNOB, including serving GNOB and neighboring GNOB. Uplink AOA is using an array of antenna elements at the GNOB to estimate the incoming angle. As the figure shows, if the incoming angle is from theta, each element is expected to have a phase response for the incoming waveform, and it is using this phase relation between different antenna elements to have a proper estimate of the UE direction. It's worth noting that it's applicable to both 1D and 2D array. When there are 2D array, the angle is decomposed into azimuth and the zenith domain, so that the 3D positioning is also possible for planetary antenna array at the GNOB side. Downlink AOD is another positioning method, angle-based positioning method that relies on UE to measure multiple downlink reference signals transmitted from the GNOB, from the TRP. It actually, downlink AOD can be determined based on the overlapped coverage of adjacent beams, where the relative power difference between beams can somehow be interpreted as a signature of the angle. So the GNOB or the TRP has the radiation pattern across different beams, and multiple beams may have overlapped coverage on a certain direction. When UE takes the measurement of multiple PIS beams, and they take the measurement or calculate the received signal strength difference or the relative signal strength between different transmission beams, those measurements can be fed into an engine to compare with the radiation pattern to help identify which direction UE is located in. So in general, this is based on a search algorithm that the angle is finally determined to be the one on which the relative radiation pattern matches the measured relative received power or the received signal strength. The last one is the multi-RTT positioning. It involves multiple cells to do the RTT measurement. Take a pair of TRP and a UE, for example, and the TRP and the UE will calculate its own RX minus TX time difference, and the PRS and the TRP will transmit the PRS, and the UE will receive the PRS, and likewise UE will transmit the uplink SRS, and the TRP will receive the SRS, and the propagation time can be easily obtained by adding the two RX minus TX time difference up. And for each TRP, UE pair will draw a circle or spherical surface at the center of the location of the TRP, and multiple circles or spherical surface will create the intersection, which will be used to locate the UE. So this is the summary of all the positioning method except including ECID, because ECID is more of fingerprinting and there is no geometry-based positioning. I think everyone would be familiar with some kind of RSRP or RF fingerprinting. In general, all these positioning method relies on some signature measurement, and in addition to the signature measurement, we have a supplementary measurement that can be helpful to improve the positioning accuracy. And a supplementary measurement were further added in release 17 to add more functionality to the positioning method. To get the measurement to support a specific positioning method, it also relies on the positioning reference signal or the pilot. Different measurement has its source of how this measurement is done. The source can be SSB or CSIRS, downlink PIS, or the positioning SRs or MIMO SRs. So next, we will introduce some key features of NR positioning from release 16 to release 18. So first one is the positioning pilot or the reference signal that were introduced in release 16. So the positioning reference signal needs to have a high capacity of multiplexing, which means that you need to have a capability of multiplexing multiple reference signals at the same time. For example, for downlink PIS, you need to multiplex multiple TRP to transmit the reference signal at the same symbol, but they somehow are orthogonal to each other to reduce interference from one another. In addition, you should have to facilitate large delay T/over estimation, because for positioning, it's unlike communication. Sometimes the UE or the neighboring, UE needs to measure the reference signal from the neighboring TRP, or the neighboring TRP needs to measure the reference signal from a non-serving UE. So the propagation delay may be large. So considering two facts, in order to increase multiplexing capacity, we define the COM-based structure. So this COM-based structure is the occupied, assuming an OFDM signal, the occupied subcarrier are grouped into multiple adjacent sets of subcarrier on which each reference signal is occupying, so that different TRP may occupy different colors of subcarriers, so that they are orthogonalized. However, considering this COM-based structure, it creates some problem, because this COM-based structure is in frequency domain, is repetition in nature in time domain. Then in this particular case, it will create some side lobe if we do the traditional correlation-based algorithm to find the first path. How to resolve that? Because if you take a look at the picture, this is a typical 3-path channel profile. If there's COM1, it's very clean. You can find where the first path is. For COM2, you can see the repetition and create some confusion where the first path is. But in case of COM6, it's very difficult. If you look at the correlation figure, it's very difficult for a receiver to tell which is the first path. So to overcome this, LTE introduced the staggering pattern. The staggering pattern means that on different symbols, the same reference signal or the pilot maps to different subcarriers on different symbols. So if you combine all those symbols together, it somehow creates an equivalent COM1 structure. And in LTE, this structure is interpreted as the staircase, because in general, this RE on cross symbol follows some form of a straight line. But the NR adopted a new staggering pattern, which is referred to as non-staircase staggering pattern. And this has additional benefit if we consider some receiving processing benefit. So let's take a first symbol. It's a COM12 structure. And if you combine the first two symbols, it is equivalent to a COM6. It eliminates most parts of the side lobes. And if you combine the first 4 symbols, it creates equivalent COM3 structure. And if you receive the whole 12 symbols, it is equivalent to COM1. So this non-staircase staggering is actually offering an opportunity at the receiver side to combine the first few symbols to create a smaller equivalent COM structure as early as possible. This may facilitate the receiver to do the quick processing when it is finding the first path. So the SRS is following the same structure. In release 16, the positioning also enhanced with the beamforming structure, which has been adopted in NR, because in NR, the first release, both frequency range 1, which is sub 7 gigahertz, and frequency range 2, which is between 24 gigahertz to 71 gigahertz, have been adopted at NR simultaneously. So some enhancement have been proposed for positioning to support beamforming towards a neighboring TRP, because for positioning, neighboring TRP is anyway needed, because usually even for the frequency range 2 high frequency millimeter wave, it's very challenging to position a UE using a single TRP. So how this can be done? Let's use this example. Assuming in the millimeter wave that UE would do the beam-based transmission of SRS. And if there's no such beam alignment procedure, that UE will transmit its uplink signal using beam sweeping manner. And from TRP side, it doesn't know where the UE is. It will also use the beam sweeping manner to receive the corresponding SRS. For example, the first round TRP using its first beam, and the second round TRP will use the second beam. In the third round, and TRP will use its third beam, and so on. But this is less efficient because it knows that that the TRP is located in a certain direction from a UE, and the UE is also in a certain direction of the TRP. Unnecessary beam sweeping is less efficient. So in release 16, this beamforming has been achieved by some kind of a beam alignment procedure. So assuming there is some prior information on how this direction is, how the TRP, on which direction TRP reside and on which direction UE inside with respect to UE and the TRP respectively. Then from UE perspective, when UE transmits the first SR, it knows they're transmitting SRs towards the first TRP. And when the first TRP is receiving the first transmission of SRs, first TRP knows that what RX beam I should use so that the beam alignment is automatically achieved. And for the second transmission, and the UE transmits the second TRP, and the second TRP is using the RX beam towards the UE, and the third and fourth. And in case some receiver diversity or the beam diversity is required, the TRP may try another adjacent beam so that the UE transmission is not missed or misdetected due to the beam direction uncertainty. So that this effectively improves the beam sweeping efficiency. And when the UE targeting transmission towards specific TRP, that the power control can be also optimized for the beam-based transmission, so that the transmission power can be adjusted on a per TRP basis. But the SRTX timing, there were also a discussion on the timing, but finally the timing is based on the serving cell only. In the release 17, to driven demanding the need of high accuracy in the RIOT, that it is identified that the UE TX RX or UE TX and RX and TRP TX and RX timing error with respect to the baseband to the RF, this group delay is the key problem to further reach high accuracy, which is why the TX timing error mitigation has been studied and specified in 3GPP, in which the TEG timing error group was introduced. To reduce the efforts of understanding how TEG works, we simply draw an example of how a TEG concept would correspond to. So for the first figure, when the 2SS transmission take uplink as an example, the 2SS transmission using two different UE antennas and corresponding to two different RF chains. The two different RF chains have a different group delay between the BB and its RF. And for this particular case, UE is doing time compensation so that its RF transmission time for the two transmissions are somehow aligned within a certain margin, in which case that these 2SS transmission is regarded as timing error free, or the timing error is within a certain margin, can be treated as simultaneous transmission. So that these two SRs, if received by different TRPs, is somehow treated as synchronized from UE perspective, so that the TDOA is possible. But for this latter case, for the right-hand side case, when there are a different group delay at the different TX chains, that the two SRs transmission from its RF point are not aligned. So in this case, these two SRs are not belonging to the same timing error group. And UE could also notify network that these two SR transmissions are not in the same TEG, are not in the same timing error group. So that when network receive when TRP receive SR1 or SR2, they cannot be simply simply subtract from each other to cancel the because in that case, additional group delay error between the two transmissions cannot be ignored. But somehow there are other mechanisms or solutions to overcome this scenario by implementation. But some information from UE side to tell the network that these two SRs are not aligned in time is also helpful from network to further take some action on how to process the receiving measurement from the TRP with respect to these two SRs. In release 17, for indoor deployment, that there are other limitations that encountered during the actual deployment. For example, for indoor GNOB, the antenna array is not very large, usually using a linear array instead of a planary array. So in this particular case, in the linear array, what TRP can measure for the AOA measurement, what TRP can measure is actually these measure beta, but this beta is not equivalent to the real AOA because there are some connection between the zenith angle of arrival for this case. So how to overcome this? 3GPP developed a method to somehow rotate the coordinate system so that this angle estimated beta is interpreted as the ZOA in the local coordinate system, where the local zenith axis is coincide with the global y-axis, which is aligned with the GNOB antenna array. For this particular case, when GNOB take the local ZOA measurement and report to the coordinate network, it will give it information that the UE is lying on the surface of the cone centered by the local z-axis. And using multiple TRP measurement, that we can still get the UE location via the traditional geometry-based positioning fix method. Also, in the indoor environment, the antenna size is very small. So then in order to improve the angle estimation accuracy, a large antenna spacing may be deployed. But the problem is that large antenna spacing, for example, larger than half wavelength, there may be a problem with the side lobe. Let's take a look at the one wavelength antenna spacing. Apart from the main lobe, there is also another side lobe. So for example, when UE is actually located in this direction, GNOB or the TRP may not be able to identify which actual UE location is from this direction or from that direction. So 3GPP developed a method to allow TRP to receive to report multiple angles, because TRP itself cannot simply resolve the angle ambiguity. And this angle ambiguity can be resolved by the location fix engine for the locations, for example, the location server, so that the true UE location will be concentrated in terms of the will be coincide with one lobe when combined multiple TRP measurement, but the false UE location is not the convergence as the true UE location. Other features like expected angle of arrival in the GNOB ARP area were also standardized in 3GPP. For downlink AOD enhancement in release 17, we know that the release 16 that the AOD is based on the receive power, but in case of multi-pass scenario, that the different paths may be strengthened by different TX beings, so that we want to know the geometry-based positioning only cares about the first path, which is the line of sight path. So the AOD is enhanced to support the first pass strength reporting to overcome a multi-pass scenario, so that the path-specific AOD can be determined primarily for the first pass, which is the lost path in this particular case. And we also specified a very detailed GNOB beam pattern to help the UE or help the location server to transfer the measured path strength difference or the relative path strength to the actual angle. And in order to facilitate to improve efficiency of the UE reporting of the measurement, the system data on the adjacent beam indication can also be provided to the UE, so that UE knows when UE is have the PRS2 or the beam 2 as the primary beam located towards itself. It can know that I could probably take priority over the adjacent beam of the PRS2, which is PRS1 and PRS3, because they may have more power than the other beams. So that you will take the measurement, report the measurement of PRS 1, 2, 3 to the coordinate network, so that the location server will be able to efficiently use 3 RSRP or RSRP measurement to find the angle of the UE. Release 17 also introduced the unloss mitigation algorithm by allowing UE or the GNOB to report loss and loss indicator or loss and loss probability to the coordinate network, so that the coordinate network can associate the loss and loss probability for a specific TOA or AOA or power measurement to further exclude those links that are identified as a high probability of unloss link. In addition, location server may also provide the loss and loss indicator for the TRP. For UE-based positioning, when UE is doing position calculation for its own. But the RMF can provide such information based on its prior information of the course UE location. The loss and loss probability can take either soft or hard value based on some implementation method. 3GPP does not specify the method how to obtain the loss and loss probability, But there are various algorithms. For example, you can use AI, artificial intelligence, to identify the loss and loss probability, or you can also compare from TRP side. You can also compare the measurement from multiple antenna elements to check whether this profile is prone to loss or unloss. Here is our evaluation submitted in 3GPP during release 17. It can show that with the loss and loss indicator, if you compare 312 or 311 to the 313, it can be shown that the positioning accuracy can be improved to less than 5 meters for that particular case. And this loss and loss identification developed by Huawei can approach the ideal case where the loss ideal loss and loss is from the channel is directly fed into the location engine. So this loss and loss identification is can be very helpful and very accurate in terms of identify the loss of link. Release 17, the last feature is the inactive state positioning, and the inactive state is introduced in 3GPP, which is between the connected idle state, so that UE can suspend communication service due to data inactivity to conserve energy. And the small data transmission can be used to support small volume data communication without entering connect state. And for positioning purpose, this is very beneficial for the UE to conserve power when doing positioning. So we'll just quickly scan the slide so that when UE is doing in inactive state, it remains to have a initial bandwidth part for the basic communication service, if any. But in case that UE will receive the PIS or SIS outside the initial bandwidth part, some switching time may be needed for UE to do the ivory tuning. And all this procedure have been specified in 3GPP. Now it comes release 18. There are 4 directions to be discussed in this slide. One is in the low power high accuracy positioning. There are various use cases as introduced in the previous slide. There are 9 use cases, but finally 3GPP have picked the use case 6, which corresponds to horizontal accuracy of less than 1 meter, and the positioning interval is between 15 seconds to 30 seconds, and the battery life is expected to be 6 months to 12 months. The main target scenario is indoor factory, and the target FR1. And by the power, 3GPP is now doing the power evaluation for positioning only, including both uplink positioning and downlink positioning. For uplink positioning, the UE will ramp up, will wake up from a deep sleep or ultra deep sleep and doing synchronization and then transmit some uplink reference signal for the TRP to receive and then go to sleep again. For downlink part, the UE will wake up from a deep sleep state and doing the PRS measurement. And then if there is no report to the network, UE will go to sleep. If there is some measurement report required, UE can using the small data transmission to tell the network. Now 3GPP are still studying LPHAP, including power evaluation, and identify the potential bottleneck and the limitation to meet the LPHAP requirement. And the second enhancement is the bandwidth aggregation. Based on the Cramer bound analysis, high accuracy positioning usually requires larger bandwidth. However, supporting positioning bandwidth of more than 100 megahertz in frequency range 1 needs to have bandwidth aggregation because for communication service, single carrier can only support 100 megahertz for frequency range 1. So there are multiple bandwidth aggregation scenario. First one is the intra-band contiguous aggregation, where the multiple component carriers are within the same band, but as well, and they are also adjacent to each other. There are very small gap up to the 0 gap. And we also did some evaluation for this particular case. It can show that under high loss probability or low loss probability, using the aggregation can efficiently improve the positioning accuracy to less than 1 centimeter, less than 10 centimeter at 90%. The other 2 use cases are intraband non-contiguous aggregation and interband aggregation. So the key feature of the intraband non-contiguous interband aggregation is that the 2 transmission bandwidths are not adjacent to each other, which creates some difficulty in terms of the RF capability. Now, 3GPP have been studying the frequency aggregation in RF aspects, and the intraband contiguous case will be prioritized in the study. And it can be feasible if it uses the single chain TX and RX structure, which means that the single chain is used to transmit both component carriers or for the bandwidth aggregation. Next one is the carrier phase positioning that's still under studying in release 18. The carrier phase positioning will be introduced in the RTK and being studied, also potentially study the feasibility to be introduced in cellular networks. This is the TX-RO. It has a very high frequency oscillator. After propagation at the receiver side, it's a shifted version of the TX. And there is a local RX local oscillator. It has an initial phase offset between the TX. And the carrier phase measurement is the phase difference between the RX local oscillator and the propagation of the RX from the TX oscillator. So it can be generally seen that this carrier phase measurement has some dependency, or has some information on the propagation delay. We also see that the Cramer analysis of carrier phase positioning can be analyzed, which is dependent on our frequency, which is larger than traditional TOA-based positioning method, which is depend on the baseband signal bandwidth. And however, in this, for carrier phase positioning, stringent requirements is needed between TRPs, so that for example, the carrier phase measurement at the UE between the two TRP is directly reflected into directly determined by the distance difference between the two TRPs. But this is maybe too stringent for the network deployment. So the positioning reference unit with its own location can be deployed to help correct the inter-TRP synchronization error, which is similar to the RTK station developed in GNSS industry. Now, 3GPP RAN working groups are still studying and evaluating carrier phase positioning, including the RF aspects, related requirements, and some ideal, non-ideal factors, and including GNOP ARP error. Here is our evaluation to see how GNOP ARP error affects the overall carrier phase positioning method. We consider FR1 3.5 GHz with 100 MHz reference signal transmission. It can be seen that in ideal case, when there's no GNOP ARP error, the positioning accuracy can be less than a couple of millimeters. But when with the present GNOP ARP error, the performance degrades significantly. The last one is the side-link positioning. So traditionally, we have the UU at the downlink, which is TRP transmitting, UE receiving, and uplink is UE transmitting and TRP receiving. And the side link is the communication link between the two UEs, usually using the uplink time slots. For the side link positioning, it's addressing the in-coverage scenario where a pair of UE are both in the network coverage, and the partial coverage scenario where one UE is out of coverage, another UE is in network coverage, and the totally out of coverage scenario when both two UE have no network connection at all. And the 4 use cases I also identified, including vehicle to everything, V2X, industrial IoT, commercial, and public safety, and the corresponding requirement in terms of horizontal accuracy, vertical accuracy, ranging distance, and ranging angle have been settled in RAN working groups. And we also showed some initial evaluation for V2X highway scenarios. It can be seen that with the 40 megahertz bandwidth currently available for ITS spectrum, the achievable accuracy is about 1 meter to 3 meters. But with a 100 megahertz bandwidth, it can less than 1 meter is possible. So currently, 3GPP is still studying the evaluating those 4 use cases to check whether the corresponding requirement can be met and at which cost, and specify the enhancement to meet the corresponding requirements. Thank you. That's all for my presentation. Thank you for your attention. It's your time now.
Yes. So
okay,
maybe I share the screen so that I can. Yeah. Let me share the screen. Actually, I'm in the meeting room and with my colleagues. So the second one. Okay.